it's still working. I
think it's because he's trying.
Can you stop the recording?
It's
Stop.
cloud. It's cloud recording.
Oh,
It's working on the cloud,
Okay,
but it
all right.
doesn't say.
okay. Yeah, so as you see, I only have a couple slides. That's because I want you doing rather than listening. But let me just give you a brief overview of what we're doing. And so this is presented on behalf of myself and xFitter and CTech and others. And Peter Risse, who is in Peter's in a superposition between JLab and SMU, is going to help out a little bit. But I thought we'd do a little bit of Sherlock Holmes. And let's make this go away and hide this. Take a case study of the strange case of the strange PDF. Come on. There we go. Oops, too far. All right. So how do you get the strange quark? And the problem there, fundamentally, the proton's made of up and down. The up is plus charge, down is negative charge. And the next slide is one is a strange quark. And so the problem is you're looking for the strange quark, which is this line, and the down quark is about 5 times bigger than that. And they both have negative charge. It's easy to separate the positive negative charge but how do you get the strange quark? It's always buried underneath the down quark. And so at Fermilab, the NUTEV and CCFR experiments found a good way to do this. What you do is neutrino deep inelastic scattering. So you take a neutrino, you hit it on a nuclear target, and then in the case where you hit an S quark, you turn it into a charm. And then about 10% of the time, the charm will decay semi-leptonically, it'll emit a muon. And then what you do is you count the number of opposite charge muon pairs versus the total number of muons you get out. And roughly that gives you a ratio between the strange and down. And the down will also, down goes to up, but the difference is the charm is heavy, and that can give the muon a significant PT, and you get an isolated muon in the case of charm, whereas typically you don't get that in the case of the down. So that's how they get that's how they got the strange quark underneath the down. Otherwise, you're trying to measure something very small underneath a ton of background. Even better, they had a sign-selected beam. So they could do a neutrino beam, but also an anti-neutrino beam. And so they could get the anti-strange and the same process, and they could actually look at that difference. So that was a very nice experiment. And what they found in general was that you expect, the up and down quark surveillance, and but then there's a bunch of anti-up and anti-down that you'll hear about next week from Tim Hobbs. And typically, because the strange quark is heavier than the up and down quark, you expect it to be suppressed. And so what they found was that in general, the strange quark was about a half of the, or we could talk about SBAR, the anti-strange quark was about half of the anti-up or anti-down, which is sort of what you expected. And that was fine. Oops, joking around too much. That worked very well, but when they went a little bit further in starting comparing charge current processes with neutral current processes, the challenge here, I should add, the challenge here is when you're doing with neutrinos, neutrinos have very low cross sections. To first order, the Earth is transparent with neutrinos. When you're doing an underground neutrino experiment, you've got as many upward neutrinos that traverse all the way through the Earth from downward. So you need a very dense target, so they use either lead or iron for this. And then since we were interested in proton PDFs, we wanted to correct that back to proton, so we wanted to do the nuclear correction. And when we did that, for charge current, neutral current measurements, we got different curves, the red and the blue. And so I refer to that as a split personality problem. What's the correct nuclear correction? So for example, if you do neutrino nucleon to a charge particle, that involves a charge current, you get the red curve, whereas if you do a neutral process where you say an electron in, electron out, that gives you the blue curve. And that's the cartoon there. We got these two different answers. And so on top of this, the strange quark is already hard to get, but because, we had to do it on a heavy nuclear target and correct it back to proton, that was a double problem. So for many years, we puzzled over that. And, one question you can ask is when you're measuring it on a heavy target, all this stuff is traversing through nuclear matter. Maybe that affects it. In one case, you're probing it with a photon that's neutral. So, that only, that won't, that'll interact differently than if you have a W boson, which is charged. And so maybe the propagation through the nuclear matter makes a difference. And we puzzled over this for a long time. But then at the OHC with Atlas, that opened up a new kinematic region, and we could look at this from another point of view. Specifically, if you look at W and Z production, what you can do is you can say, for example, for Z production, typically that comes from UU bar or DD bar, that's a neutral particle, and the strange contribution to that is SS bar. So it's quadratic in the strange quark distribution, but the W is linear. It's S with U or S with C, something like that. And so, roughly speaking, if you make a ratio of these cross sections, one's linear, one's quadratic, you're going to get approximately the strange quark distribution out of this. And here's a cartoon of the strange quark distribution for the W plus rapidity versus the OHC. And here is a ratio. It's the ratio basically of S plus S bar over twice the D, or effectively what this tells you is, as I said before, you expect because the strange is heavy, the strange on average is about half the D bar or half the U bar. And that's what people expected, and that's what they measured from the fixed target experiments. And now we got to Atlas and said, gee whiz, we've got, we don't have to do the nuclear correction anymore because we can measure this on a proton directly. We don't have to do this on a heavy iron or lead target. So we can get this very cleanly, and we'll nail it down. It's quite a bit of variation. What they did in 2012 when they took their WZ ratio data, what in fact they got was 120%. They found out that if I compare just the S bar to the D bar, the S bar was larger than the D bar. And this is certainly counterintuitive. If anything, you expect it to be smaller, it's heavier. But that's what they found. Okay. And so that's what we're going to try to do. That's what we're going to reproduce for a couple of reasons, because we're going to run this. We're going to run this with the fixed value of this ratio down here where the fixed target likes it of about a half. And then we're going to open it up and let it float and see what the Atlas data likes. And we're going to find out that comes out about 110%. And we're going to see that reduces the chi-squared. And then at that point, that's the warm-up. And then you can play with that. So this was a very surprising result. There's been a bit of history since then, but we won't worry about that. But this is what we're going to try. And so let me give you a tour very quickly of what's on the web. So if you pull up here, if you just open this in a new tab, what you'll see is there's lots of things here. There are lots of things here, but probably the most useful, this is the overview. Okay, this is a link to the Docker instructions. Be careful, this is all the data files. We don't need this. That's half a gigabyte of data files if you want to do everything. But in here, this is extra material. This is FRA 2023. This was the presentation by FRA Julie, who actually helped me create the Docker file. And then this is the manual, Minuit manual, and some Python things. So if you pull that up, and I won't go through this, but in FRA, what he detailed there in the code we've given you, there are 8 separate examples. And so you can take a look at them. We've got proton, we've got pion WZ production, We've got Pion PDFs, Pion fragmentation. Here's the list of exercise, a whole bunch of things. You can explore those. But what I want to do today is just take you through this strange distribution, which is exercise 6. And it's got two subdirectories. In one case, we fix this value. In one case, we let it be free. And then we'll use xFitter to fit that. And then xFitter draw will actually take that output, put that together, and compare. And then what we'll do on Monday, Monday is the second part, we'll just play around with some PDFs. So I have some Python-based things, an OHA PDF, and some other things, and we'll do that. So that's the basics. If you do the basics and you're happy, then you can take off. If you want to explore more, we can help you with that, and that's where we're going. Let's see, to get you started on the Docker, you should be able to pull down the Docker, and then in this, make this a little bit larger. Yeah, in the Docker, you should be able to fire up the Docker. And if you want, it's optional, but if you want to be able to sort of connect to a local directory, you can set that up here. You'll have to set up your own home directory, but then you can go ahead and run that. And essentially, the basic commands are to let's see, where's the setting up a container. Essentially, all you have to do is you source the setup, and then it's useful to export this path. That way, xFitter is defined everywhere. And once you have that, I think I have a working version up here and